We're finally to the part where we can really compute limits algebraically. And so we're going to figure out how to do that today. We saw at the end of class last time, if we are working with a polynomial or rational function and we are able to plug the number in to the problem, then computing limits is really easy. We just plug the number in and we're done. The problems that we're going to deal with today are going to be problems where we can't plug the number in because we get 0 in a denominator. And we have to figure out how to work with that. Okay, so when we see a limit, our first thought should always be just plug x in, whatever that number is. See what happens. If we get a number out that doesn't have a 0 in the denominator, we're good. Otherwise, we have to worry about what to do from there. And that's what we'll focus on today. So our first step here, plug 1 in. We see this limit. So if I plug 1 in, I get 1 plus 1 minus 2 over 1 minus 1, which gives me 0 over 0. Okay, so this is a problem. We have 0 in a denominator. So we can't just say this is undefined. We can't say it doesn't exist. We can't say we just stop. We have to figure out what to do. Getting 0 over 0 indicates to me that I should be able to simplify something in the original expression. The fact that there's a 0 in both the numerator and denominator means that there should be something that can cancel out. And so that's going to be our goal. This is what we're going to see with all the problems today, is that we're going to start out with 0 over 0, and we're going to do some kind of simplification. It looks different depending on the problem. So in this one, I want to go back and I want to simplify this original expression. And to me, it looks like I might be able to factor. In the denominator, I can factor an x out. I'm left with an x minus 1. In the numerator, it looks like I can factor x plus 2 times x minus 1. And look at this, I can cancel an x minus 1 out. That's beautiful. Notice I'm rewriting the limit throughout this problem. You need to do that. I am going to take points off if you don't. So just be wary of that. So now we're left with x plus 2 over x. Okay, now that we've canceled something out, we can try plugging our number back in and see if we no longer get 0 in a denominator. So if I plug in 1, so I'm going to plug in x equals 1 and see what happens. I'm going to get 1 plus 2 over 1, so I get 3. And that's my final answer. Notice that after I plugged 1 in, I no longer wrote the limit there, okay? So I write the limit in until I plug the number in and get a number out, okay? So factoring is a good example of what's happening in these types of problems. Oftentimes factoring is a useful trick to do, okay? The reason that we can do that, we can do this process, is because this function and this function are equal to each other everywhere except for at x equals 1. X equals 1 is not in the domain of this original function, but everywhere except for x equals 1, they're equal to each other. And remember, limits only care what happens near 1, not at 1. And so near 1, these two functions are equal, which means that their limits are equal as well. Okay. So this is that property that we were just using. So if I have two functions that are equal except for at a single point, then their limits are going to be equal. Okay, this is going to be a property that we use a lot without like writing it down or necessarily even thinking about it. Okay, so why don't you try this next problem on your own? It's going to use a slightly different technique, but that's okay. I'm going to work it as well. So we start out, every time we start out by plugging our number in. In this case, I'll plug in 0 for each. So I'll get 4 plus 0, which is 4 squared minus 16 over 0. Once again, I notice I'm getting 0 over 0, so I have to do more work. The 0 over 0 indicates to me that I should probably simplify. Okay, so I'm going to go back to my original expression. It doesn't really look like I can factor super nicely here, although if you're creative enough, you could actually factor this. But to me, it looks like I could probably expand that numerator a little bit. There's nothing in the denominator that can be simplified. It's just a plain old h, so I have to do my simplification in the numerator. So let's FOIL this out. And remember that we're going to get a middle term. This is not just 16 plus h squared. You have to treat this as 4 plus h times 4 plus h. So when you multiply that out, you're going to get 16 plus 8h plus h squared minus 16 over h. We notice that the 16s will cancel out. And then in the numerator, we can factor an h out. So we're left with 8 plus h over h. H's cancel out. Remembering we're rewriting our limit throughout each step of this problem until we plug our number in. Okay. This looks like it's pretty much as simplified as I can get. I've canceled things out. So now I'm going to plug in 0. When I plug in 0, I get 8 plus 0, which is 8. That's my final number. Okay, so we're noticing there are multiple techniques we can use. We factored, now we FOILed. That's really going to be the hardest part, is figuring out what technique to use in a particular problem. So I'm going to give you really kind of all the different techniques in this video today, and then you're going to have to be able to identify it. But the real trick is you're just simplifying things. We're doing algebra. The algebra is the hard part in these problems, not the calculus. The calculus is easy. It's just plugging numbers in. The algebra is the hard part. Okay, so now we notice this next problem. We plug -1 in. We have -1 squared, which is 1 plus 8. So that'll give me 9 minus 3 over -1 plus 1. So once again, I get 0 over 0. So getting 0 over 0 should tell us that we should simplify things. So we simplify. Okay, now I have to figure out how in the world to simplify this original expression. Okay. There is going to be a trick called multiplying by the conjugate. You have maybe seen this in a pre-calculus class, but you might not. And so multiplying by the conjugate is going to allow us to get rid of square roots. So the way that this works is we keep our original expression. And then what we do is we multiply. We're going to multiply both the numerator and denominator by the same thing, because that won't change our problem. We're going to take that piece that has the square root, and we're going to keep the square root the same. And then all we're going to do is we're going to change the sign between the two pieces. We're going to make this +3. And I have to multiply the denominator by the same expression. Otherwise, I'm changing the problem. So notice that multiplying the numerator and denominator by the same thing is the same as multiplying by 1. This whole expression is just a very strange way of writing the number 1. Okay, so now I have to figure out what to do here. Still rewriting the limit because I haven't plugged anything in yet. The denominator is not going to simplify nicely at all. The denominator did not have any square roots in it originally, so I am not going to do anything with the denominator. I'm going to leave the denominator as y plus 1 times the square root of y squared plus 8 plus 3. Okay, this is going to be a trick in this like multiplying by the conjugate type of problems. One piece, either the numerator or denominator, does not get simplified at all. If you multiply this out, you are going to get stuck. Okay. So now in the numerator, this was the piece that I was trying to simplify. I was trying to get rid of the square root here. So if I distribute things in the numerator, I notice I have a difference of squares. I have something like x minus a times x, x plus a. Okay, like this whole piece is my x and the 3 is my a. So remember, when I multiply a difference, x minus a times x plus a, if you multiply this all out, this is a difference of squares, x squared minus a squared. Okay, you can also just multiply it out and see what happens, but this makes our life a little easier. So in this case, I should get x squared, this thing squared, which is y squared plus 8. The square root goes away because I've squared things, minus a squared. A was 9, so minus 9. Okay, this is good. We got rid of the square roots in the numerator. Okay, y squared plus 8 minus 9 is the same thing as y squared minus 1. And let's go ahead and factor that out. This problem actually has a lot of pieces in it. It's a little messy. Y squared minus 1 factors as y minus 1 times y plus 1. And this is where things get good, because now we can cancel a y plus 1 out in my numerator and denominator. Okay, notice I have been writing the limit throughout all of these pieces. Now I'm going to go ahead and plug -1 in, so I no longer have to write the limit. When I plug -1 in, I get -1 minus 1 over the square root of 9 plus 3. Notice that this is a plus down here now, which is good. So I get -2 over 3 plus 3 is 6, or -1/3. Okay, so that trick we saw when we saw a square root, we multiplied by the conjugate. Okay, that's a good thing to remember. So we've factored, we've FOILed, we've multiplied by a conjugate. Okay, like I said, in this video, we're learning really all these tricks. In class, we're going to put them all back together and see if you can identify which trick to use and where. Okay, this one we've got a fraction over a fraction and fractions being subtracted. So when we plug the 5 in, we're going to get 0 over 1/5 minus 1/5 is going to be 0 again. So we need to simplify. And really just ask yourself, how would you simplify this expression? If I asked you to simplify it and give you no other instructions, what would you do? You would probably combine the fractions in the denominator. And that's what I would do. So I'd find a common denominator here. Our common denominator is going to be 5x. So I have to multiply this guy by x in the numerator and denominator. And this guy I have to multiply by 5 in the numerator and denominator. And so now I can combine these into a single fraction. I get x minus 5 over 5x, x minus 5. Now I have this double fraction here, which is not so pretty. So I'm doing algebra here. All I'm doing is algebra, okay? If you're getting stuck, it's because you don't remember your algebra facts, okay? So this is why we do pre-calculus and algebra, so that we can put it all together in calculus, okay? So I multiply by the reciprocal of this guy, because that's how dividing fractions goes. So the reciprocal is 5x over x minus 5. The beauty now is that these cancel each other out. So we're left with a limit as x approaches 5 of 5x. Now we can plug our 5 in and we get 25 out. Okay, lots of examples, okay? One last example where we have absolute value and we have to figure out what happens. So once again, if I plug that -2 in, -2 plus 2 is 0, and we're going to get 0 in the numerator as well. So we're going to have to simplify. You might notice that we can factor a 3 out in the numerator. And you're tempted to cancel the x plus 2's out, but the one has an absolute value and the one doesn't, so we have to figure out how to deal with that. The thing to be careful about here is that absolute value breaks apart into two pieces. So absolute value breaks apart into a positive piece and a purely negative piece, okay? And it's going to be positive if x is bigger than or equal to -2. -2 is the place that this is equal to 0. So this is the place that things break apart. And it will be negative if x is less than -2. Okay. The thing we have to worry about here is that -2 is that part that we were worried about, which means that absolute value of x plus 2 kind of breaks apart into two separate pieces, depending whether we're working on the right of -2 or the left of -2. So we're going to have to break this apart into a left and right hand limit, which is oftentimes what we have to do with absolute values. Okay, so we're going to break this apart into a limit as x approaches -2 from the right and a limit as x approaches -2 from the left, okay? We still have that 3x plus 2 in the numerator, regardless of what we're doing. If I'm working to the right of -2, so I'm plugging a number in bigger than -2, then the absolute value gets replaced just with x plus 2. If I'm working with a number smaller than -2, then the absolute value, which would be to the left of -2, then the absolute value gets replaced with -x plus 2. Okay. We notice in each of these cases, the x plus 2's cancel out. In the top case, I'm just left with 3. In the bottom, I'm left with -3. So the right-hand limit gives us 3. The left-hand limit gives us -3. These are not equal to each other. So our overall limit does not exist because the left and right-hand limits were not equal. Okay, this was a lot in one video, a lot of different techniques. The goal here is to remember when we get 0 over 0, when we plug a number into a limit, we simplify. And that simplification can take lots of different forms, but really it's just using algebra, okay? And so we'll see a lot more examples in class and hopefully make this make more sense.